Hi everyone, this lesson is about using a method of numerical integration known as the midpoint rule. So we have a formula here for the midpoint rule which looks awfully complicated, but when we break it down it's not that bad. And the idea behind this is that we have a function. I've drawn my function here, f of x in green. Now my function that I'm using in this example is 1 over x, a lovely function. And I want to find the integral from 1 to 6 of my function. And I could use analytical processes, but today I'm going to use the midpoint rule. I'm going to divide my region from 1 here over to 6 into 10 small rectangular regions. So n equals 10. And the width of each of these little rectangles then is the upper limit. We usually refer to that as A and B, what you can see there. So the upper limit in my case is 6. Subtract the lower limit of 1, divided by 10, the number of rectangles. And so each of my rectangles will have a width of 0.5. W is the width of the strip here. That's nice. Now I need to find the height of the strip. I suppose I should tell you that the first value here of x is referred to as x naught. This next one is referred to as x subscript 1. This one would be x subscript 2, and so on, all the way across until we got to here. This one would be, in our case, x9, and in this case, x10. Because we're using n equals 10, we'll finish on x10. More generally, this would be referred to as x subscript n, and this one would be x n minus 1, where n could be any number. We don't have to use 10 rectangles. We could use 100 rectangles if we wanted a more accurate answer. The idea of using rectangles is, if we look at this second one for instance, we know that the rectangle height here, it's a little bit low. We've lost a little bit of area there, but we've added a little extra bit there. So we're hoping that it compensates. Now it won't be exact. This is an approximate formula. And the little discrepancies that are introduced by the curve, well, if the rectangles were thinner, the discrepancies would be less. And eventually, if the rectangles were very, very thin, almost infinitesimally thin, the discrepancies would tend towards 0. And so this ends up becoming a type of a Riemann sum. Now, we're not actually going to take limits, we're just going to do the calculation. Well, let's see how we would go with working this out. So there's the example that we just talked about. Now, what would we normally do? Well, we would do like I've just said up there in the diagram. We would talk about the fact that we were given A equals 1, B equals 6, and N equals 10. We would calculate the width of each of our strips as B take A over N, 6 take 1 over 10. I'm being a bit repetitive. We did this already, didn't we? Now, what's my formula? Well, the integral from 1 to 6 of my function, it's approximated by W, the width of the strips, multiplied by the sum. Now what are we looking at? We're looking at the midpoint. So in the first instance, we're looking at halfway between x0 and x1 as an x coordinate to substitute into my function to calculate the height of this rectangle. So I could write here x0 plus x1, but that's not so great. I'm going to write xi plus xi plus 1. I'll have to find the halfway point between those. Now what does this I represent? I represents just a counter. I will count from 0. If I starts at 0, then that evaluates to be x0 plus x1. In other words, the edges of the first rectangle. I'll make a note here that I must start at 0. When I equals 1, this will read x1 plus x2, which is going to find the midpoint of my second rectangle. Where do I want this to finish? I want this to finish with reading x9 plus x10. So, or more generally, I want this to finish with I equaling n minus 1. Now that's the general version of the rule. Let's get more specific. We know that w in our case is 0.5. We will have sum from I equals 0, in our case, to 9. And our function, now this is where we need to get a little bit trickier. I can't just write xi. I have to give my calculator something more specific to work with. Now let's think about the values that xi has to take. Xi in this case starts at the value 1. So I'm just going to write down what xi needs to be. Xi will start at 1. Then it will be 1.5. Then it will be 2. All the way up, the last value that I want is 5.5 because this represents the left-hand edge of my rectangles. Now, if only there were an easy way to calculate the numbers 1, 1.5, 2, etc. Well, there is. The idea would be to say we're starting from 1 and we are adding 1/2 for every value of I. Let's just put that in a little set of brackets there. I may need to give myself a bit more room. That's going to, as I ranges from 0 to 9, that's going to generate the sequence of numbers 1, 1.5, 2, 2.5, all the way up to 5.5, which are the numbers we need for xi. The left-hand edges are going to start at 1, finish at 5.5. What about the right-hand edges? These right-hand ones represented by xi plus 1. Well, they start at 1.5 and they finish at 6. So I'm going to have to write a formula that starts at 1.5 and increases by 0.5 every time. There it is. That's going to be the way that we can calculate this thing out. Now let's get the graphing calculator going and we'll see how we do this on the graphing calculator. Where am I? I'm in the middle of something. So this is actually where I need to be. The first thing I want to do is enter my function into y1, the variable y1. If I draw that thing, oh, that's not very good. Let's just go back to the normal sized window for a minute. There it is. So that looks a little bit like my graph from x equals 1 to 6. This is the area we're dealing with here. So I could there you go. That's better. So this is the bit that I'm looking for. That's lovely. Now let's just pop back to the normal calculator screen. I've got a whole bunch of stuff there which I will just delete. Oh, come on, make that go away please. Okay, all good. Now what was the formula we were trying to use there? Oh, what have I done? Yes, that's right, I want to see that. Just move that over a bit so I can still see my calculator. Try this again. Hopefully we can still see what we're doing. So I start by entering 0.5. Multiplied by. I need sigma notation. This is under F4, the mathematics menu. Then to the right, then sigma. We jump in here. Now I've used F to represent my function. In the calculator I have to put y1 and I find that under the variable key. Then the graphing, these are variables, the graphing variables, and then here we go, y1. I'll even put a little pair of brackets, just like my brackets are for the function. Inside here I have, whoops, missed. Inside the red brackets I want to have a quotient, and I want to have 1 plus 0.5i. Let's try another little pair of brackets. 1 plus 0.5, and I'll literally put I there, alpha I, as a variable. Close those green brackets, plus new pair 1.5, plus 0.5i. Where'd you go? There it is. Close the brackets. So that gives me my lower and my upper limit on the rectangles. all divided by 2, right arrow gets me to here, and this is where I get to tell the calculator variable I goes from 0 to 9. And there's my answer, 1.782. Let's write that down. This is approximate, 1.782 units squared. I really should have had approximate all the way down here because this is an approximate rule. Now let's just see how well we did. You may have noticed when I was, whoops, didn't mean to go there. You may have noticed when I was using the maths menu earlier that there's an integral function. I can tell this, I can ask this to do the integral of 1 over x from lower limit 1 to upper limit 6. And there's the true answer. If we worked this out analytically, we would have had the number 1.79. We got 1.82. That's pretty close, and especially that we've just used 10 rectangular strips. Look how large these chunky corners are here. So we could of course increase the accuracy of this process by using more strips, more of these rectangles, and then we'll get an answer to any desired degree of accuracy we like. Okay, that's enough for now. That's the end of our little video. Thanks for watching.